Hello everyone. My name is Nova Estrera. I'm a secondary college student with a course of Associate in Aviation Electronics Technology. This time, I am doing a solo activity in midterm module 1 activities. Number 1. How do you distinguish between positive and negative logic systems? Prove that an OR gate in a positive logic system is a NAND gate in a negative system. So the binary variables, as we know, can have either of the two states, the logic 0, or the logic 0 state, or the logic 1. So these logic states in a digital system such as computers, for instance, are represented by two different voltage levels or two different levels. So if the more positive of the two voltage or current levels represents a logic 1 and the less positive of the two levels represents a logic 0, then the logic system is referred to as a positive logic system. So if the more positive of the two voltage or current levels represents a logic 0 and the less positive of the two levels represents a logic 1. Logic system in which logic 1 is assigned to the higher voltage and logic 0 to the lower voltage. So negative basic system is a logical circuitry in which higher voltage level refers to low 0 or false. And lower voltage level refers to high 1 or true. So to change a positive logic gate to a negative logic gate is to complement all inputs and output of the gate at the same time. So a positive logic NAND gate implements the function of x, y, and hence a negative logic NAND gate implements x, y is equals x plus y, which is NOR function. So let's have the number 2 questions, which is give brief statements that would help one remember the truth table of AND, NAND, OR, NOR, XOR, and XNOR logic gates functions. Irrespective of the number of inputs used. First, we have AND gate. AND gate is a logic circuit having 2 or more inputs and 1 output. So the output of an AND gate is high only when all of the inputs are in high state. So in all other cases, the output is low. So when interpreted for a positive logic system, this means that the output of the AND gate is a logic 1. So only when all of its inputs are in logic 1 state, in all other cases, the output is logic 0. Let's have the next exploration. So we have the AND gate. Let's see. So the truth table is like this. Input 1, and we have also input 2. Next is output 1. Don't forget there and 1. So for this table, the AND gate is so named because if 0 called false and 1 is called true, so the gate acts in the same way as a logical AND operator. So the following illustration that table shows is the circuit symbol and logic combinations for an AND gate. So in the symbol, the input terminals are at left and the output terminal is at right. So the output is true when both inputs are true. Otherwise, the output is false. So in other words, the output is 1 only when both inputs 1 and 2 are 1. So next, let's have the NAND gate. So NAND gate operates as an AND gate followed by a NOT gate. So it acts in the manner of the logical operations and followed by negation. So the output is false if both inputs are true, and otherwise the output is true. So next, we have the OR gate. So OR gate gets its name from the fact that it behaves after the fashion of the logical inclusive OR. So the output is true if either or both of the inputs are true. So if both inputs are true, so if the both inputs are true, if both inputs are false, so and then the output is false. In the other words, for the output to be 1, at least input 1 or 2 must be 1. Next, we have NOR gate. NOR gate, this is a combinations of OR gate followed by an inverter. So its output is true if both inputs are false. So otherwise the output is false. Also the output is false. Next is the exclusive OR gates. It's not good. So exclusive OR gate acts in the same way as the same the logical either. So the output is true if either but not both of the inputs are true. So the output is false if both inputs are false or if both inputs are true. So another way of looking at this circuit is to observe that the output is 1 if the inputs are different and it has a both 0 if the inputs are the same. Let's have the last gate, logic gate. So the last logic gate that we have to explain is the exclusive NOR gate. So that's what it is. And the table is input 1. So the exclusive NOR gate is a combination also of exclusive OR gate followed by an inverter. So its output is true if the inputs are the same and false if the inputs are different. So let's have the last questions of this activity, which is why are NAND and NOR gates called universal gates? So justify your answer with the help of examples. So for the explanation, so we have OR and NOT gates are the three basic logic gates, as they together can be used to construct the logic circuit for any given Boolean expression. So, NOR and NAND gates have the property that they individually can be used to hardware implement in a logic circuit. So, the NAND and the NOR gate can be said to be universal gates since combinations of them, the operations, and can thus produce an inverter, an OR gate, or AND gate. So, the non-inverting gates do not have this versatility since they can produce an invert. So non-AND gates are called universal gates because all the other gates can be created by using these gates. This is known as universal gates also because they can perform all logic functions of OR and NOT gates.